Let me give a brief recall from the previous two talks. So the following is our setup. So we start with the finite quiver Q, and we fix a two-sided ideal I of the path algebra KQ, and we denote the quotient algebra by A, so namely this KQ mod I. And then by Choki-Solotas result, we know they exist reduction system satisfying diamond condition for the ideal. And once we fix the reduction system satisfying the diamond condition, then we have irreducible paths, right? So by irreducible paths, I mean the path in Q which does not contain subpaths in the S, in this S, okay? And then by Bergman diamond lemma, we can identify the vector space spanned by the irreducible paths with the algebra A. So we have and this isomorphism is induced by the natural projection, right? If we have a path, then we look at the image in the quotient, and we denote the inverse by sigma. So somehow sigma send an element in A to the normal form. So we should get a like linear combination of irreducible paths. Okay. From the reduction system satisfying diamond condition, we can construct A infinity algebra we call it PQR, and we also get the A infinity quasi isomorphism from this A infinity algebra PQR to the classical Hochschild-Coltrane complex. And on the left hand side, it's a DG Lie algebra. The bracket is given by the Gerstenhaber bracket, and on the left hand side, the A infinite structure is constructed by homotopy transfer theorem. So we transfer the Gerstenhaber bracket on the right hand side to the left hand side. So we get a higher Lie brackets. In order to study the deformations from this L infinity algebra, we need to look at the following space in degree 0, in degree 1, and in degree 2. So in degree 0, we have the home space of KQ0 bimodule from the arrows to the algebra A. And in degree 1, we have the home space from the from S to A. And in degree 2, we have the home space from S3 to A. And here S3 is the set of all overlaps. So by overlap, I mean so it's a path which contains two subpaths in S, and there should be overlap. So this means they have a common non-trivial path. Okay. And so now we can use L infinity algebra to we can compute the Mollet-Cartan element for this L infinity algebra. So the Mollet-Cartan element lies in this space in degree 1, right? So we take so then we pick an element, but formally, so this means G1, G2 is in P1 QR. So this just means the home space from KS to A. And then in order to study to check the Mollet-Cartan equation, we should first introduce a combinatorial star product. So we denote by star G. So this star G is defined using rightmost reductions. Here, rightmost reduction means if we have a path and we can contain subpaths in S, then we can perform reductions by replacing the subpath S by Fs. And the rightmost just means we always choose the rightmost subpath in S and replace this subpath by F. So this means this is the rightmost reduction. And once we have this combinatorial star product, then we can check the Mollet-Cartan, G is the Mollet-Cartan element, if and only if the star product is associative with respect to for any element in the overlap. So here W1, W2, W3 is a path in S3. So this means here W1, W2 is in S2, and W2 W3 is in S2, and the W2 should be should pass a non-trivial path here. Okay, so this means then we can split these three subpaths, and we get this these two different star product. Okay, so this associativity, right? This is just associativity identity. And moreover, if G is a molecular element, then by the L infinity quasi-isomorphism, GK, and we can send the molecular element to a molecular element in the Hochschild-Kochen complex, right? And as by the general fact, the Hochschild-Kochen the molecular element in the Hochschild-Kochen complex gives a star product, gives an associative product, namely here. So this means if we denote the left-hand side by like A star prime B, then A star prime B should be associative because G is a molecular element. And actually by computation, by direct computation, we check the left-hand side also equals the combinatorial star product. So in particular, this implies the combinatorial star product is associative. Okay. And also we can talk about homotopy equivalence or gauge equivalence of two molecular elements. And then for the L infinity algebra, this notion of homotopy equivalence is just given by computing the molecular element in the big L infinity algebra. So here tau in degree 0 and d tau in degree 1, and this is just the DG commutative DG algebra with differential determinant by sending tau to d tau. Okay, and if we have molecular element for this L infinity algebra, then we can take tau to be 0, d tau to be 0, and we get a molecular element for PQR tensor T. And if we take tau to be 1, d tau to be 0, we should get another molecular element of PQR tensor T. And then we say these two molecular elements are homotopy equivalent. And actually, similar to the molecular element here, the molecular element for this big L infinity algebra can also be described in a very combinatorial way. So this means essentially, in order to compute the molecular element, essentially we need to compute the L infinity bracket between elements in P0 QR and P1 QR. Okay, so but the L infinity bracket between these two spaces is also has also a combinatorial description. So somehow, in practice, maybe for some specific example, we can compute the molecular space explicitly. Okay, by using this idea. Okay, as an inclusion, we get the deformations of the reduction system. I mean, up to homotopy equivalence is equivalent to the deformations of the associative algebra A. Why this for the left-hand side? Actually, we should look at like the molecular space associated to the L infinity algebra, right? PQR. But this molecular space just describe the deformation, the formal deformations of the reduction system. Because if we have a G, an element G, we can change the reduction system R by sending S to Fs plus this GS. Okay, here. So then we get the and we can talk about like we can say, okay, the formal reduction system is like formal satisfies some kind of a formal diamond condition, right? So this gives a deformation problem for reduction system, and this deformation problem is controlled by by the L infinity algebra PQR. Okay, and as we know, we have a L infinity quasi-isomorphism between PQR and the Hodge-Coulson complex. So, and this induced the isomorphism between the Mollet-Cardon space. Okay. Okay, so this what we discussed in the previous two talks, and let me give a remark. So in general, the combinatorial star product is an infinite sum, right? It's just the formal power series of T. Even G like is a polynomial. It's just like here, if G, even G is just have a G1T, G2T squared. So if we have only finite, even we have a finite many terms, this star product might be infinite sum. So we are interested in the following question, for which G is a star product, always a finite sum for any A, B. Okay, so, and in this talk, in this lecture, we try to look at this question from two point of view. So the first idea, we use some idea of from noncommutative Gröbner basis. So we can choose this G in a subspace, not the whole space PQR, just a subspace. And this subspace somehow depends on so-called admissible order on the path in Q. So later I will give the notion, the definition of admissible order. Okay, and the second idea, we can still start with the formal star product G, like G here, pick G element G in the whole space, but we can take small values of T, like we can take T to be 1 or maybe half, and maybe in this case the star product is well defined, right? It's we have a finite sum. Okay, so then we can define this. Okay. So okay, then let's give the definition of algebraization. For this, I need the definition of algebraic deformation. So algebraic deformation is just a KT algebra, AT star, and such that the star product is just the original product for the constant. Okay, and here the underlying space is just AT, and this means we give a new product on this polynomial algebra. Okay, so this looks like formal deformations, but we just replace the formal power series by polynomials. And we have an observation, right? An algebraic deformation defines the formal deformation, right? By taking the completion, right? We can complete this KT algebra, right? By in this way, right? Okay. And yeah, I think the notion of algebraization is goes back to Artin in 69. So this so an algebraization of formal deformation is an algebraic deformation, and such that the completion is isomorphic to our AT star as a formal deformation. By this I mean, by isomorphism as a formal deformation, I mean it's these two KT algebra, AT and A prime hat, are isomorphic as a KT algebra, and which restrict to A is the identity of A. Okay. And let me give a remark. So if we have a formal deformation AT star, and such that the star product always lies in the polynomial ring for any AB, then this AT star admits somehow an obvious algebraization. Namely, we can just take AT together with this star, right? Because this star is well defined, right? Here can be restricted to this subspace. Okay, but in general, the converse need not hold, because the reason is here. When we define the algebraization, then you will find the notion of algebraization is invariant on the gauge equivalence, right? So this so this means there might be a formal deformation which has an infinite sum, the star product has an infinite sum, but it might be homotopy gauge equivalent to a formal deformation whose star product is finite sum, right? So we can find, it's very easy to find a example for this. Okay, so let's look at the first point of view with respect to the question. So we start with a PBW deformation. Okay, so now let's go back to quiver with relations. So now A is just KQ mod I, and we fix a reduction system R satisfying diamond condition. And then we have the following observation. So if we pick G in PQR, so namely in the home space from S to A, and satisfying the following condition. So GS always GS lines in this subspace of the path algebra. So here Q smaller than S, I mean the subspace subset of paths whose length strictly smaller than the length of S. Okay, and the sigma is just we just take the normal form of an element in A. Okay, so this is just the inverse of the natural projection, right? And if G satisfies this condition, we know star GT is finite, right? We only get the polynomial of T, because when we perform reductions using F and G, the length the length of the path should decrease, so it should stop, right, when we perform reductions. Okay, so somehow this means the new reduction system is reduction finite. So this star product should be finite. Okay, and if we further assume GT is a Mollet-Cartan element of our L infinity algebra, then we should get a natural algebraization of the formal deformation AT star GT. Okay, just restrict to the polynomial algebra. Okay. So, and for this algebra, we can take values, right? Like we can take T to be 1, and actually we can take T to be any lambda in K. Okay, and then we still get the associative product here. And in this case, the associative product, the associative algebra on the left-hand side is isomorphic to another quiver with relations here. Okay, so we just change the idea by minus lambda GS. Okay, for each S. Sorry. Yeah, here. So let's denote this by AG lambda. Okay. And yeah, if I the ideal is homogeneous, I mean with respect to the path length, and if G satisfies the length degree condition, and GT is the Mollet-Cartan element, and then this algebra is as we see. So then we have this algebra, right? And we also have this isomorphism. And actually, in this case, this algebra is just a PBW deformation of A. And by PBW deformation, I mean so this AG lambda here is a filtered algebra. So we look at the associated graded algebra, and which should be isomorphic to A. So this is the definition of PBW. Okay. And in this case, the Mollet-Cartan equation of the L infinity algebra coincide with the Blauermann-Gazzoli criterion, which is a very useful criterion in PBW deformations. But in the context of a reduction system, yeah, we just need to check the Mollet-Cartan equation. So it's equivalent to check this criterion. Okay, so this equivalent. And yeah, sorry, here I should remind you this isomorphism. Yeah, actually this isomorphism is just given by identifying the irreducible path, because here left hand side we have a basis given by the irreducible path, right? The image of irreducible path, right? And on the right-hand side, we also have a basis given by the image of the irreducible path. Okay, so we can identify this, and so we should get like isomorphism of vector space, and then we transfer the product here, and we get exactly this star product. So somehow this means this identification is exactly it's a algebra isomorphism. Okay. And let me give you an example. So let's look at the polynomial algebra. So probably you have seen from the first talk. This polynomial algebra is also given by can be given by quiver with relations, right? Namely, we look at the quiver with one vertex and n loops, and the relation is just the commutative relation, namely here. And then we can choose a natural reduction system satisfying diamond condition here. And now we pick a G, and which send xj xi to be a linear combination of xk. Okay, so here cji up k is just a scalar in the field, in the base field. And then we find gt is a molecular element of the infinity algebra if and only if this is a Lie algebra. So we have a Lie algebra structure on the space spanned by the arrows of our quiver. Okay, and the bracket is given by this one. Okay, so we send xj xi to this sum. Okay, so somehow this cjik is just a constant, right? The structure constant of the Lie algebra. And moreover, in this case, the star product, okay, the associative product given by the star product is isomorphic to the universal enveloping algebra of this Lie algebra. Okay, and similarly, this isomorphism is given by identify the irreducible path. Okay, we send the irreducible path here to the same irreducible path here, because the irreducible path, the image of irreducible path form a basis for these two vector space. Okay, and this is the isomorphism of algebras. And actually, in this case, the star product can be expressed using conservative graph without cycles. And you will see more details in the next talk. And actually, in this case, this G, this molecular element G, induce so-called Lie-Poisson structure on the affine space, or n-dimensional affine space AN. Okay, and more generally, we can look at the combinatorial star product for some special Poisson structures, right? Okay, so anyway, this you will see this in the next talk. Okay, so now so this just so for this PBW deformation, somehow we have some order, right? We give order for the path, and this order just given by the path length. But more generally, we can give a more general order. So this is called admissible order. So this by definition is a total order on the path, and satisfying the following condition. So for every non-empty subset of Q, should have a minimal element, and also this admissible order should be compatible with the multiplications. Okay, so look at here. So like if P bigger than Q, then PR should be bigger than QR. Okay, and similarly, if P bigger than Q, then RP should be bigger than RQ. And also here, this looks like the path length degree, right? Okay. So now, we go back to the KQ mod I, and we fix the reduction system satisfying diamond condition. So here R is should satisfy diamond condition. Okay. And then we fix the admissible order on Q, and such that the Fs should lies in this subspace. And here Q smaller than S just means the subset of paths which are strictly smaller than S with respect to this order, this admissible order, okay, for each S. And then we can choose G satisfying the following condition. So we just look at G satisfying this condition, okay? So GS also lies in this space for each S, okay? We just look at this subspace, okay? We just so G is just in the subspace. And then if G satisfies this order condition, we know similar to the PBW case, this dot product should be a finite sum, right? Because once we perform reductions, the order of the path should decrease. So it should stop because because here we have a minimal element, okay. And then we have a proposition similar to the so this proposition is completely similar to the PBW case. So we just replace the path length by this admissible order, okay, here. Sorry. So if GT is a Morley Cartan element, and then this formal deformation admits algebraization. So this is obvious algebraization, right? Because this star GT is well defined, okay, in this case. And moreover, we can take value for this T, like to be lambda, and then we should get algebra isomorphism. And this algebra isomorphism is given by identifying the irreducible paths, okay? So this, okay, why we need this? Because if we use this, we will get more deformations. I mean, more deformation than PBW deformation, okay? So let me give you an example. So let's look at the so-called deformed quantum preprojective algebras. For this, let's just look at the extended thinking quiver of type A and theta. So this quiver contains n plus 1 vertices, and we consider the double quiver of Q. So this means so here alpha 0, alpha 1, alpha 2, alpha n. So it's the arrow are the arrows in Q, and then for each arrow we add the inverse arrow. Like here alpha 2, we add alpha 2 bar. Okay, so this is the inverse arrow here. So this is called a double quiver. And then we look at the preprojective algebra. So this is given by the path algebra of Q bar here, and modulo the preprojective relation. So so this preprojective relation is given for each vertex. Like look at the vertex 0. So we have this path alpha 0 and alpha 0 bar. So this path parallel to this E0, right? Alpha 0, alpha 0 bar. And we also have a path alpha n bar and alpha n. So we look at the difference, okay? And for this preprojective algebra, we have a natural reduction system satisfying diamond condition. Namely here, we just pick the first entry to be S, okay, here, and take the second entry to be Fs, okay. And you will find this reduction is reduction finite, because when we perform reductions, we just move this bar from right to left, right? It should stop, right? Here, you see the bar here. The bar here is on the right, and then we move to the left, okay? And so you will check this reduction finite, and then by Bergman-Diamond lemma, you know, because in this case we have no overlaps. So then by Bergman-Diamond lemma, we have a so we know this reduction finite and the reduction unique. So this means it satisfies diamond condition. Okay. So anyway, so this is very easy to check. And then we give a admissible order, which is determined by the order on the arrows. Okay. And I mean here determined by I mean, it's determined by so-called lexicographic order. Okay, determined by this given order. And then we can say that we look at all the G satisfying the order condition. Okay, and then we find G has the following forms. So here we have a lambda I, because this lambda I just corresponding to the PBW deformation, right? Because the length of EI is strictly smaller than S, alpha I bar. Okay, but using this admissible order, we also get this mu I. Okay, because the length of alpha bar I minus 1, alpha I minus 1 is smaller than this one. Okay, strictly smaller, right? And so this G, yeah, satisfy the length degree. Okay, and then because as I said, there is no overlap, so any element in this space should be a Mollet-Cardin element, right? Because we don't need to check. So I mean, the Mollet-Cardin equation is trivial, right? So then we get the associative product. Here we get the formal deformation, okay, associated to GT. And also because this G satisfies the length, the order condition, so this means this star GT should be a finite sum. Okay, so it is just a polynomial about T. Okay, the star product. And then this means we have algebraization, obvious algebraization. Okay, this. And actually, by if we look compute the gauge, the homotopy equivalence, actually we can just take all the mu I to be 0 except mu 0. Okay. So then we denote mu Q by mu 0 plus 1. Okay. And then we can take T equals 1. Then we get the actual deformation of pi Q. So this means this algebra has a basis given by the irreducible path. Okay, so this is the infinite dimensional algebra, right? Let me remind you. Yeah, it's obvious maybe for you, but if you look at the irreducible path, then we know there are infinite many irreducible paths, right? Because we can go alpha bar, right, many times, and then go use alpha, right, many times. Okay. So anyway, so we have a nice basis for this algebra. So this so-called deformed quantum preprojective algebra. Okay, and actually, if Q equals 0, then this just a deformed preprojective algebra, which was introduced by Crowley-Bowie, Holland, and if Q is arbitrary, then which was studied by Martin Clark in his master thesis, and also by Crawford in his PhD thesis. Okay, and this algebra is very interesting. I think in both in representation theory and also in geometry. Let me give you some remark, which I think it should be interesting. So if we take Q equals 1 and take all the lambda I to be 0 except lambda 0, and then here we make lambda 0 to be a formal, so we denote, we view lambda 0 to be just a formal parameter T, and then we get this, we look at the algebra around E0. Okay, so we have this, so here E0 is here. Okay, we look at the algebra along this vertex, right? And then we know this actually is a deformation quantization of the symplectic structure on the singularity. Okay, which we start with. And we can also, like, now if we take lambda I to be 0 for all I from 0 to n, so this means here we have no PBW deformations, because here is 0 and 0. And we take arbitrary Q, okay? And then we still look at the algebra around the vertex E0. And you will check that this algebra actually is isomorphic to the quantum hypersurface here. So this is the non-commutative algebra, right? Because, and yeah, sorry, if Q is not 1, right? But if Q is 1, right, we get just this AN singularity, right? Because Q equals 1, then we have a X, Y, Z is a commutative variables. And then we have this this hypersurface, okay? So you will see we don't change the hypersurface, just change the commutative relation, okay? And I think in the last talk we will also mention this this example, but from more geometric perspective. And also in the last talk you will see more applications of algebraization with respect to some admissible orders in algebraic geometry and non-commutative geometry. In particular, like we will talk about the non-commutative resolution of some singularities, and we will mention like reconstruction algebra, which was introduced by Michael Wims. And we will study the deformations, commutative deformation and non-commutative deformation, and also actual deformations, okay, for this example in the next talk. Okay, and yeah, so now I would like to study the deformations. Somehow I would like to study the deformations of monomial algebra, but with respect to some fixed admissible order. Okay, so for this for a monomial algebra, I will introduce a variety. So this variety was introduced by Green, Hiller, Scholler, and I will give the definition later. But before this, let me introduce some notation. So if I have a element in the path algebra KQ, we define the tip of X, just the path appear in X, which has the maximal length, okay, with respect to this order, okay, here. And then we look at the then for generally we if we have a subset of KQ, we denote the tips of the subset in this way. So we look at all the tips of X, of the element X in X except 0. Okay. And so here's the definition of the variety. Okay, but a priori it's not a variety. So it's just a set of algebras with the form KQ mod I. Sorry, here S should be here. Okay, I should remove this part, this assumption. Okay, S is just this minimal relation of the monomial ideas. And then we look at we can define this KQ mod I, and I is just idea of KQ, and such that the two-sided idea generated by this tip I here, right? We replace X by I, coincide with the two-sided idea generated by this S. Okay. So somehow this means the algebra in this set, like KQ mod I, has a reduced non-commutative global basis G, whose tips are just S. Okay. And in this paper, yeah, here you can click the green box, and you will find the link of this paper. Okay. In the handout version. And So there is a theorem by in this paper. They proved actually this set is an affine algebraic variety, and so this means this set is given by solution given by some equations in some affine space. Okay, and actually, if we actually this you will see the dimension of the algebra in this set are the same, right? Because we have somehow we have the same irreducible paths as basis. So this means we can use somehow. This means the algebra in this variety is the deformation of this monomial algebra. I mean, the actual deformation of the monomial algebra, right? So yeah, actually we can this affine algebraic variety can be given by the Mollet-Cardan equation, so of the L infinity algebra. Okay, but here the finiteness condition just make sure like these equations we have only finitely many equations. Okay, this is a very natural condition. So about the irreducible paths. Okay. Yeah, I will not give the detail, but yeah, later I will give you example to look at this. Okay, so yeah, before giving the example, let me mention some properties of the variety. So actually, the algebras in this corresponding to point in this variety share many common properties. So like all algebra in this variety have the same dimension, right? I think this is clear because as I said, the algebra in this variety just actual deformation of the monomial algebra, right? The initial monomial algebra. And also you will see the, yeah, okay, here's the A. So if A is a finite dimensional, yeah, and then all algebras in this variety have the same Cardan matrix. So Cardan matrix just means a matrix with entry ij is just the dimension of ei aej. Okay, we look at so this means just the number of irreducible paths start with ei and ends with ej. Okay, so this entry of the matrix in ij. Okay, and why this we have the same Cardan matrix? Because our star product, if you look at the star product, we will find the star product preserves the idempotent. So this means the star product, so the deformation does not change the dimension of ei aej. Okay, so actually, if we have a deformation of A, and this also induces a deformation of ei aei. Okay, so this the property of our star product. Sorry. And also we can the result, yeah, say to compare the global dimension in this variety. So somehow the global dimension in the of the algebra in the variety are bounded are upbound by the global dimension of the monomial algebra. Okay, and then if the global dimension of the monomial algebra, the initial monomial algebra is finite, and then the Cardan determinant conjecture holds for all algebra in this variety. Okay, so this looks very interesting, right? Somehow, in order to check the Cardan determinant conjecture, it's enough to look at the the variety starting with the monomial algebra whose global dimension is infinite. Okay. Yeah, by Cardan determinant conjecture, I mean the statement is that for a finite dimension algebra with finite global dimension has whose the Cardan matrix has a determinant 1. Okay. And the last, there is also result by about quasi-hereditary property. So if A, I mean the monomial algebra is quasi-hereditary, then all algebra in the variety are quasi-hereditary. Okay. So actually, there are more properties in this paper, common properties, but I just list these 5. Okay, let me give you an example. So we start with this quiver. Okay, we have a L, A, B, C, D, E, F, G, H, I, J, K. And then we give an order determined by this by the order on the arrows. Okay, we set A bigger than B and bigger than C and so on. And we pick the minimal relation of the monomial ideas to be AB, here AB, and also BA here, and also CBI here. Okay. And then by the in the paper, so this example from this paper, and they compute the Green-Hiller-Schioler compute this variety just given by these equations. Okay, so this in 5-dimensional affine space. And okay, we can let me show you how to use the Mollet-Cardan equation to get this one, this equations. So now we pick element in this PQR1 integrally 1, right? So namely the home KSA, and then we look at all the possibilities, right? Like AB, so CDEF bigger than smaller than AB, so we can pick these 2 elements, right? Satisfying the order condition, the admissible order conditions, okay? And also we can pick this, okay? And in particular here, GH is somehow this looks like a PBW deformation, right? Because this the length of here the length is 2 and here the length is 3. Okay, so we have only one PBW deformation here. Possible PBW deformation, right? We have to check the Mollet-Cardan equations. Okay, and then you find actually we have only one overlap for this S3. Okay, here, right? We have only ABI, overlap ABI, and then the Mollet-Cardan element. So in order to check G is the Mollet-Cardan element, it's enough to compute this. The star product is associative for this S3. Okay, and you will find the left-hand side is 0 because when we compute the star product of B and I, we get 0 because here G send BI to be 0, and also the initial reduction system send BI to 0 as well. So we get the 0 on the left-hand side. And if we look at the right-hand side, and then we compute AB first, and then we can use a regional reduction F, then we get 0, right? Because AB sent to 0, and then we use this new reductions G, and we get CD plus EF. Okay, here, and then we compute the star product with I. And then you will find this equation. Okay. Okay. So yeah, so I have 10 minutes. So I will in the last 10 minutes I will mention talk about the second idea. So namely we can still start with formal deformations, and then try to evaluate T for small values. So for this, maybe we have to work on the field of real numbers or complex numbers. Okay. Before talking about this, the general result, let me give you an example. So we look at the following quiver with relations here, and so here we have a natural reduction system for this ideal, which satisfies the diamond condition. So it's very easy to check because somehow this so this reduction finite because we we reduce longer paths to smaller length paths, right? So short paths. And you will check there is no overlap between for this reduction system. And now we can pick any element in PQR. Like you can pick this one for example. And then we will check, because we have no overlap, so this G satisfy the Mollet-Cartan equation, right? Namely, the Mollet-Cartan equation is trivial in this case, right? Because we have no overlap. And then we can compute the star product in this case, like for A star B C, and we get a formal power series, right? And actually, like for if T small enough, we get this, right? We get this like rational functions. It's 1 over 1 minus T squared. Okay, and we can take value, right, for lambda, like for lambda to be any scalar, and now we denote the algebra induced the algebra given by the new quiver given by quiver with new relations here, right? A regional one we have AB minus D, but here we should add this one, and then we take T to be lambda, so we get this. And for this one, now B prime C so reduced to lambda BC, so we get this new idea. And then you say if lambda is in here, then we get an algebraic morphism, right? Because if lambda is not 1 and minus 1, we know the star product is well defined, right? Here. And here we also have a algebra, and in this case we have algebra isomorphism, and this isomorphism, yeah, similar to the PBW deformations. This algebra is given by identifying the irreducible paths, right? Because both of the algebra have a basis given by the image of irreducible paths. But for if lambda equals 1 and minus 1, the new reduction system is not reduction finite. So we have to change the reduction system so somehow for these 2 points, okay? But yeah, and also for this case, so yeah, we have no this isomorphism because the left-hand side is not well defined, okay? Okay, actually we find somehow this this phenomenon, it's very can be generalized to any quiver with the relations. So yeah, let's say the result. So if we start with any algebra, not necessarily finite dimensional, so just any KQ mod I, and we fix a reduction system satisfying the diamond condition and also satisfying this the length condition. So here S the absolute of S just means the path of S, and so we have this condition. So here the absolute value of Fs just means it's just the maximal length appearing maximal length of the path appearing in Fs. Okay. So we should add this condition if yeah, if we pick a Mollet-Cartan element in this infinity algebra and also satisfy this kind of condition, this length condition, and we also assume GS is a polynomial in T for each S. I think this is the natural, right? Because if GS is a like a formal power series, then yeah, as we said, it's in general we should also get a like very strange formal power series, right, for the star product. So yeah, let's just we should I think this condition it's natural, okay. And then under these conditions, we can prove the star product has a rational function in T at coefficients, okay, like here, right? So this is the example, right? You can, of course, here we only compute A star B C, but we can also compute like A B prime star C, and in this case it's 0. Okay, so somehow we only get this one rational function here. Okay, and if A is a finite dimensional algebra here, and then the study is convergent on the neighborhood of 0, because by this result we know there are only finitely many rational functions appearing in the star product, right? Namely, because we have this the finite dimensional algebra, so we have only finitely many irreducible paths, and here the rational function just the coefficients of the irreducible paths, right? So we have only finitely many rational functions, and this means we have only finitely many poles, and then this means we can find a uniform bond, right? We can find a bond, and the star product is convergent in this region smaller than this bond. Okay. And actually, this the above result is motivated from a open question on the convergency of conservative star product, so which is like a formal a star product for quadratic Poisson structures. I think we will talk about this in the next talk. We will also mention like convergent result for quadratic for some quadratic special quadratic Poisson structures in the next talk. Okay, and so at the end of the talk, I would like to ask a question. So what about the infinite dimensional case? Okay, so here compared with the first remark, we know the study is always convergent near or near 0, but what convergence properties does a study have, right, when A is infinite dimensional? And for this, I think we might try to prove like the number of rational functions appearing in the star product is finite. I mean, up to polynomials. Or maybe you can prove, like maybe it's not the number of rational functions. It's not finite, but maybe the number of poles are finite. Right? So anyway, so this our ongoing work. So yeah, thank you very much.